This video explains why E equals mc squared means everything you believe about nuclear physics and atomic energy is built on a comfortable fiction, and what actually happens when atoms release their power through nuclear fission and fusion will restructure how you understand matter, energy, and existence itself. You imagine tiny particles orbiting like planets in the Rutherford-Bohr model of the atom, held in place by forces you learned about in school, and that picture satisfies you completely. Let me challenge that satisfaction with a question that should trouble you deeply, which is this: what exactly do you think energy is? Not what it does, not how we measure it, but what it actually is as a thing in the world. Albert Einstein's mass-energy equivalence reveals that what we call mass and what we call energy are two names for the same underlying reality viewed from different perspectives. And here is the more disturbing version of that question. What do you imagine happens inside the nucleus of an atom, that dense and impossibly small heart at the center of everything you see and touch? Believing that breaking atoms apart merely releases some stored mechanical force, like snapping a spring or breaking a lock, means you have misunderstood the nature of reality at its deepest level. Examining what actually happens in nuclear processes reveals something that changes your entire understanding of matter and energy and what it means for anything to exist at all. Learning new facts is not what this requires of you, because what it really demands is unlearning the comfortable fictions we have told ourselves about the physical world for centuries. Common understanding of atomic energy goes like this: atoms contain energy, and when we split them through nuclear fission, or fuse them together through nuclear fusion, that energy gets released like opening a pressurized container or unwinding a coiled spring. That understanding represents a failure to grasp what modern physics revealed about the deepest structure of nature, and the failure runs far deeper than most people realize. Consider this thought experiment. A piece of uranium sits in your hand, with a certain weight and a certain mass that you can measure with exquisite precision. Suppose you could take that uranium apart atom by atom, then further disassemble each atom by separating the protons and neutrons from their nucleus and scattering them to the ends of the universe where they no longer interact with each other. Weighing all these scattered particles and adding up their individual masses with perfect accuracy would lead you to discover something strange, which is that the sum would be greater than the mass of the original uranium. That missing mass was never there as mass in the first place, because it existed as something else entirely, as the binding energy that held the nucleus together. And here is what should break your intuition about all of this: that binding energy is not a force acting on the particles, because it is mass. Or rather, what we call mass and what we call energy are two names for the same underlying reality viewed from different perspectives. This is not a metaphor, and it is not a useful approximation, because it is the literal truth about how the universe is constructed at every scale. The story of how we came to understand this begins not with bombs or reactors, but with careful measurements and persistent mysteries that refuse to yield to classical explanations. Physicists in the early years of the 20th century began to weigh atoms with extraordinary precision, and by that point Ernest Rutherford had already shattered the comfortable image of the atom as an indivisible sphere. Alpha particle experiments revealed the atom as mostly empty space, with nearly all its mass concentrated in a central nucleus thousands of times smaller than the atom itself, while electrons orbited this nucleus like sparse motes of dust circling a dense stone. James Chadwick discovered the neutron in 1932, earning the Nobel Prize in 1935 for completing our picture of nuclear composition and providing the key to understanding nuclear structure. Measuring the masses of different nuclei produced peculiar discrepancies that nobody expected. The mass of a helium nucleus turned out to be measurably less than the combined masses of two protons and two neutrons measured separately, only by about 0.7%, but the instruments of that era were precise enough to confirm this was not experimental error. Classical physics could not absorb this result. Mass was supposed to be conserved, and matter was supposed to be neither created nor destroyed. Yet here was mass simply missing and vanished into something that nobody could explain. The measurements were undeniable, even though the explanation remained incomprehensible. Resolution came from a direction that seemed, at first, to have nothing to do with nuclear physics at all. From thinking about light and motion and the strange consequences of a universe where the speed of light remained constant regardless of how you moved through space, Albert Einstein published a paper in 1905 that contained, almost as an afterthought, a relationship that would reshape our understanding of matter itself. Elegant and almost deceptively simple, the equation stated that E equals mc squared, meaning energy equals mass, multiplied by the square of the speed of light. What many people miss entirely is this: that equation does not merely describe a way to convert mass into energy like converting water into steam, because it reveals that mass and energy are fundamentally identical and are different manifestations of the same physical quantity. Every mass has an equivalent energy, and every form of energy has an equivalent mass, and they are not two things that can be exchanged, but one thing viewed under different circumstances. Consider what that means. The very concept of matter as something distinct from energy turns out to be a convenient fiction, with no clear boundary and no fundamental distinction between them. What we perceive as solid and substantial and real, like the chair you sit in and the body you inhabit, is not a different category of existence from light, from heat, from motion, because it is all the same fundamental stuff manifesting in different forms. Abstract truths mean nothing unless we can see them operating in the real world. So let me make this concrete. A proton, which is a single hydrogen nucleus, has a mass of approximately 1.007276 atomic mass units, and a neutron has a mass of 1.008665 atomic mass units. Adding 2 protons and 2 neutrons together, simple arithmetic gives you 4.031882 atomic mass units. But measuring an actual helium 4 nucleus shows a mass of only 4.002603 atomic mass units. That difference of 0.029279 atomic mass units has vanished. But here is the thing. It has not vanished because it has been transformed. Multiplying that missing mass by the speed of light squared tells you exactly how much binding energy was released when those 4 particles came together and bound themselves into a helium nucleus. Energy did not come from somewhere else, and mass did not go somewhere else, because the mass became the energy since they were always the same thing. Iron 5-6 has the highest binding energy per nucleon, making it the most stable nucleus in the periodic table. This is why elements lighter than iron release energy through nuclear fusion, while elements heavier than iron release energy through nuclear fission. This mechanism powers the sun through the proton-proton chain reaction. Approximately 600 million tons of hydrogen, specifically deuterium and tritium isotopes, fuse into helium in the solar core every second, and about 4 million tons of that hydrogen simply cease to exist as mass and instead stream outward as light, as heat, as the radiation that warms your face and grows your food. The sun is not burning, and it is not consuming fuel the way a fire consumes wood, because it is literally converting its own substance into radiance. Stop and absorb that for a moment. The light falling on your skin right now was, 8 minutes ago, mass inside the sun. Not fuel that released stored energy when it burned, but actual matter whose very existence transformed directly into the photons striking your retina. What you see when you look at the sun is matter becoming light, existence itself changing form. Here is where the story becomes stranger still, where our intuitions must be abandoned altogether. When we speak of binding energy and mass defects, and the energy released in nuclear reactions, we are still using language borrowed from the classical world. We speak as if the protons and neutrons inside a nucleus are tiny balls connected by invisible springs, and that the energy is stored in the tension of those springs. But that picture is entirely wrong. Particles inside a nucleus cannot be described as objects with definite positions moving along definite paths, because they exist in a state that has no analog in ordinary experience. Wave functions, which are mathematical expressions that give only the probability of finding a particle in a particular region of space, are the only way to describe them. Until you observe the particle, it does not exist in one place, because it exists in a fundamental sense as a spread-out cloud of possibility. This is not uncertainty due to ignorance, and it is not like saying we do not know where a lost key is hiding, because the indeterminacy is built into the fabric of reality itself. The Heisenberg uncertainty principle, discovered by Nobel Prize winner Werner Heisenberg in 1927, involving Planck's constant, states that you cannot simultaneously know both the exact position and exact momentum of a particle. Before measurement, the particle genuinely has no definite position, and it is not somewhere waiting to be found, but everywhere it could be, with various probabilities, until the act of observation forces it to manifest in one location. Quantum laws govern the atomic nucleus entirely. Protons repel each other with tremendous electrical force since they all carry positive charge, and like charges repel, which means in any classical picture the nucleus should fly apart instantly and be utterly unstable. Yet nuclei exist, and they are among the most stable structures in the universe. What holds them together cannot be visualized in classical terms. The strong nuclear force operates only at extremely short distances and completely overwhelms the electrical repulsion at those scales, binding the particles together. But this force does not work like a rope or a spring because it operates through the exchange of other particles called gluons in a constant quantum dance of creation and annihilation happening at timescales so short they cannot be directly observed. Binding energy required to tear the nucleus apart equals precisely the mass defect we measured, but it is not stored somewhere because it is woven into the quantum state of the whole system. When we say the helium nucleus has less mass than its components, what we really mean is that the quantum state of the bound system, that complex and probabilistic and fundamentally non-classical configuration, manifests a different amount of inertia than the particles would exhibit separately. Consider what happens in nuclear fission, in the splitting of a heavy nucleus like uranium-235. A neutron approaches the uranium nucleus and gets absorbed. For an instant, the nucleus becomes uranium-236, and that new configuration turns out to be unstable. Quantum state deformation begins, elongating like a liquid drop, stretching toward breaking, and then it splits. Two daughter nuclei, typically barium and krypton, along with a few loose neutrons, fly apart with tremendous energy, carrying kinetic energy at velocities that seem almost incomprehensible. Those additional neutrons can trigger fission in nearby uranium nuclei, creating a chain reaction. When enough uranium is assembled to reach critical mass, this chain reaction becomes self-sustaining. That energy came from nowhere that you might expect, not from any stored reservoir, and not from any wound spring or compressed gas. Product mass measures less than the mass of the original uranium, and that missing mass, about 1/5 of 1%, has become the kinetic energy of the fragments, the radiation of photons, the motion that we perceive as heat and blast. Enrico Fermi, the 1938 Nobel Prize winner, achieved the first controlled nuclear chain reaction in 1942 beneath the University of Chicago, proving that atomic energy could be harnessed for both constructive and destructive purposes. This work directly led to the Manhattan Project and the first nuclear weapons test, the Trinity test in New Mexico in 1945. Fragments weigh less than the uranium did, not because mass was expelled as some separate substance, but because some of what was mass has become motion and existence has changed its form. 1/5 of 1% seems tiny, but here is where the arithmetic becomes terrifying. The speed of light is approximately 300 million meters per second, and squaring that gives you a conversion factor of roughly 90,000 trillion. Even a tiny amount of mass converting to energy releases energy that is astronomical by the standards of chemical reactions. Chemical reactions like the burning of gasoline or the explosion of TNT involve atoms rearranging while electrons shift from one atom to another, breaking and forming chemical bonds. Nuclei remain unchanged in those reactions, and the mass defect in chemical reactions is present technically, but so small, a few parts in a billion, that it is utterly negligible. Energy in those cases comes from the rearrangement of electron configurations rather than from any significant conversion of mass. Nuclear reactions deal with the strong force, which is roughly 100 times more powerful than the electromagnetic force governing chemistry. Binding energies are correspondingly larger, mass defects are measurable, and energy released is millions of times greater per atom than any chemical reaction can produce. 1 pound of enriched uranium contains as much energy as thousands of tons of coal, not because it is better fuel in the ordinary sense, but because it is accessing a deeper transformation, a more fundamental conversion than chemistry can touch. Consider what should astonish you about these numbers. The amount of mass converted in a typical fission reaction is roughly 1/5 of 1%. And in fusion, the process that powers the sun, approximately 7/10 of 1% of the mass becomes energy. Tiny fractions, with more than 99% of the original mass remaining as mass afterward. Yet those tiny fractions represent powers that dwarf anything humanity had previously wielded. The Hiroshima bomb called Little Boy released energy equivalent to about 15,000 tons of TNT, and it did so by converting approximately 1 gram of mass into energy. 1 gram, which is the weight of a paperclip and less than the weight of a raisin, flattened a city and killed 100,000 people when that single gram of existence transformed. Tens of times more potent than chemical ones. Radioactive decay provides another window into nuclear instability. Unstable nuclei spontaneously transform, with half-life periods that can range from microseconds to billions of years, following probabilistic laws that govern when individual atoms will decay. Any student can perform these calculations. Calculations are not understanding, though, because truly grasping what atomic energy means requires feeling in your bones the strangeness of it, the way it subverts everything common sense tells you about the nature of substance and the sources of power. Every transformation in the universe, at bottom, involves this relationship. When a candle burns, a tiny fraction of mass becomes light, so tiny that no scale could measure it, but present nonetheless. Digesting food releases chemical energy that corresponds to a minuscule loss of mass. A ball falling and striking the ground creates thermal energy of impact that corresponds to an infinitesimal mass deficit in the system as a whole. Energy is never created and energy is never destroyed. It changes form endlessly, though, cycling between radiation and matter, between kinetic and potential, between the visible and the hidden. Whenever energy becomes more concentrated, the system's mass increases proportionally, and whenever energy disperses, the mass decreases. A compressed spring weighs more than a relaxed one, not by any measurable amount, but in principle, by an amount corresponding to the stored potential energy. This is the literal truth about how mass works in our universe, not a theoretical nicety. Something should fundamentally restructure how you see the ordinary world around you, so let me share it with you now. You sit there believing yourself to be solid, feeling your own weight and the mass of your body pressing down against your seat, thinking of yourself as made of matter, of stuff, of substance, of things. Atoms make up your body, though, and atoms are mostly empty space. Stripping away all that empty space and compressing the actual nuclear matter in your body, the protons and neutrons at the centers of all your atoms would fit you inside a volume smaller than a grain of sand. Everything you think of as yourself, as solid and substantial, is more than 99.9999999% emptiness. That core of nuclear matter that remains is itself not fundamental, because protons and neutrons are made of quarks held together by gluons. Here is the remarkable part. Quarks themselves account for only about 1% of the mass of a proton. 99% of what you perceive as the solid, tangible mass of your body comes from the binding energy of the strong force from the quantum dynamics of the gluon field. You are not made of matter in any simple sense because you are made of energy bound into configurations that manifest as mass. Relationships make you up. Quantum states make you up. Mathematical patterns that nature settles into when governed by certain laws make you up. The distinction between the substantial and the insubstantial, between matter and energy, between the thing and the activity, these distinctions dissolve entirely when you examine them closely. Every time you lift your hand, you are moving patterns of bound energy, and every time you think a thought, you are rearranging quantum configurations in the neurons of your brain. The boundary between you and the world around you is not a wall between different kinds of substance, but a local pattern of organization in what is ultimately a unified quantum field. Something else is often forgotten in discussions of atomic energy. Knowledge we have gained about these matters did not come from pure reason or abstract mathematics alone, because it came from experiment, from careful observation, from the patient willingness to let nature speak and to listen even when she says things we do not want to hear. Developing quantum mechanics, the theoretical framework that describes all atomic and nuclear behavior, forced upon scientists a recognition that shook them to their foundation. That recognition was this: the ways human beings naturally think about the world, the categories we use, the concepts that seem self-evident, do not necessarily correspond to anything real at the atomic level. We speak of particles, but there are no particles in the ordinary sense, no tiny billiard balls following definite paths. We speak of waves, but there are no waves in the ordinary sense, no medium vibrating, no disturbance propagating through space. Something else exists there, something that displays particle-like behavior in some experiments and wave-like behavior in others, something that cannot be captured by either picture alone. Niels Bohr called this complementarity. Two descriptions that seem mutually exclusive, particle and wave, are both necessary for a complete account of atomic phenomena. Neither is true by itself and neither is false, because they are complementary aspects of a reality that cannot be captured in the classical terms our minds evolved to use. Working with Bohr in those early years when quantum mechanics was taking shape, I remember when I first truly grasped this principle. It was a heroic time. Not the doing of any one person, but the collaboration of scores of scientists from many different lands. Bohr's spirit guided us, restrained us, deepened, and finally transmuted the entire enterprise. And he taught us to be comfortable with contradiction, to accept that our theories are not photographs of reality, but tools for organizing experience. The Heisenberg uncertainty principle states that you cannot simultaneously know both the exact position and exact momentum of a particle. Instrument limitations do not cause this, and better equipment would not solve the problem because the universe itself does not contain the information. Position and momentum are complementary aspects that cannot both be precisely defined at once, like asking for the exact boundary of a cloud or the precise location of the present moment. Probing the nucleus encounters similar limitations at a deeper level. Measuring disturbs what we measure, and determining where a particle is requires interacting with it, which changes its momentum. Measuring momentum precisely requires spreading out the measurement in space, which loses information about position. Observer and observed are entangled in ways that classical physics never anticipated. The atom does not care that our intuitions developed in a world of medium-sized objects moving at medium-sized speeds. Atomic behavior follows its own laws, and those laws are stranger than anything we could have imagined before we were forced to imagine them. General notions about human understanding and community, illustrated by discoveries in atomic physics, are not wholly unfamiliar or wholly unheard of in the nature of things. Even in our own culture, they have a history, and in Buddhist and Hindu thought they hold a more considerable and central place. What we find in modern physics is an exemplification, an encouragement, and a refinement of old wisdom. The Bhagavad Gita speaks of the unity underlying apparent diversity, of the way reality presents different faces to different modes of inquiry while remaining fundamentally one. Modern physics discovered, through entirely independent means, the same truth. Particle and wave, position and momentum, matter and energy, these are not different things but different ways of approaching a single underlying reality that resists our attempts to capture it in any single picture. The most profound implication of all this for understanding the physical world involves a question that people sometimes ask: what would happen if we could convert mass to energy with perfect efficiency, if instead of the tiny fractions released in fission or fusion, we could transform matter directly and completely into radiation? This happens when matter encounters antimatter. When an electron meets a positron, its antimatter counterpart, they annihilate entirely, and nothing remains but photons, pure light carrying away all the mass energy of the original particles. The conversion is complete. Bringing together a kilogram of matter and a kilogram of antimatter would release energy equaling approximately 90 million billion joules, which is roughly the energy released by a 40 megaton thermonuclear weapon from 2 kilograms of mass completely converted. Antimatter exists only fleetingly under ordinary conditions, though. High-energy particle collisions create it, and it annihilates almost instantly upon encountering ordinary matter, with no way to store it, accumulate it, or use it as fuel. The universe remains profoundly asymmetric for reasons not yet fully understood, dominated by matter, with antimatter appearing only as brief, exotic visitors. That calculation still teaches us something instructive. A single kilogram of any substance, water, rock, air, or flesh, contains within it the equivalent of 40 megatons of destructive power. Energy is there, bound up in the mass, whether or not we have any means of releasing it. The chair you sit on, the book in your hand, the body you inhabit, all of it is frozen energy and vast stores of potential change, held in stable configurations by the quantum rules governing atomic and nuclear behavior. Consider what this means for understanding permanence and change. Stability you perceive around you, the endurance of mountains, the solidity of iron, the persistence of your own body from day to day, all of this stability is contingent. It depends on particular configurations of quantum fields that happen to be stable under current conditions. But those conditions could change. Sufficient pressure, sufficient temperature, sufficient concentration of energy would transform the configurations. Mountains melt. Iron vaporizes. Atoms themselves restructure. This happens inside stars. Core temperatures reach millions of degrees and pressures exceed anything found on Earth. Thermal energy of particles becomes comparable to the binding energy of nuclei under those conditions, and fusion becomes possible. Hydrogen transforms into helium, helium into carbon, carbon into oxygen, and the cascade continues through silicon and sulfur and iron until the star has converted all it can. Massive enough stars die explosively, scattering into space the heavy elements forged in their interior through stellar nucleosynthesis. Gold in your ring, calcium in your bones, iron in your blood, all of it was synthesized in the cores of stars that exploded billions of years ago. You are quite literally made of stellar ash. Atoms of your body were forged in nuclear fires, scattered across space in supernova explosions, collected by gravity into our solar system. and eventually incorporated into the living structure that reads these words. The story of atomic energy is not merely physics, because it is your autobiography written in the language of nuclei and binding energy. Understanding this gives energy conservation a new meaning. Energy is never created or destroyed, and that includes the energy manifesting as the rest mass of matter. The mass of the universe is part of its energy budget, and matter and radiation are interconvertible forms of the same conserved quantity. What have we actually discovered about the nature of reality? We discovered that the solid, substantial world is made of emptiness and binding. Atoms are mostly void, and nuclei are mostly energy manifesting as mass. Particles we call fundamental are not little objects, but mathematical entities governed by probability, and even they are made primarily of the dynamics of the quantum fields that bind them together. We discovered that the boundary between matter and energy is not a boundary at all, but a change of perspective on a single underlying reality. Mass is energy at rest, and energy is mass in motion. They transform into each other through the conversion factor that is the speed of light squared, and this transformation is not exotic or unusual, because it is happening constantly everywhere, in every nuclear process, in every star, in every galaxy across the universe. We discovered that human intuition is a poor guide to the atomic realm. Concepts that serve us well in the world of ordinary experience, like solid objects and definite positions and deterministic motion, fail completely when applied to the behavior of atoms and nuclei. New modes of thought, new mathematics, new philosophical frameworks had to be developed to accommodate what nature revealed to us, and we discovered something that weighs heavily, which is that this knowledge, like all knowledge, is dual-edged. The same understanding that explains the sun's warmth enables the construction of nuclear weapons that could end civilization. The same equations that describe the binding of nuclei describe their destruction. Peaceful applications and destructive possibilities cannot be separated because they are aspects of the same truth. This burden physicists carry now, that we shall carry always. As Robert Oppenheimer said, witnessing the Trinity test, "Now I am become death, destroyer of worlds," quoting the Bhagavad Gita. We have known sin in some crude sense, which no vulgarity, no humor, no overstatement can quite extinguish. We have uncovered secrets of nature that grant tremendous power, and power can be used for good or for harm. The atom does not care which we choose because it merely is what it is, obeying its laws, indifferent to our hopes and fears. Today, fusion reactors like ITER represent humanity's attempt to harness this fundamental force for peaceful energy production, bringing the power of the stars to Earth in controlled conditions. Yet even these peaceful applications remind us that we are manipulating forces at the very foundation of existence itself. Truly, understanding atomic energy means accepting that the universe is far stranger than it appears. The table before you is a storm of quantum probability frozen into apparent solidity by the laws of large numbers. Light entering your eyes is the distant product of mass becoming radiation inside a star. The ground beneath your feet contains enough bound energy to reshape continents, held quiescent only by the stability of nuclear configurations. Understanding atomic energy means recognizing the limitations of ordinary thought. We did not evolve to understand atoms because we evolved to understand lions and gazelles, fruit and predators, the behavior of middle-sized objects in the middle-sized world. Quantum mechanics is true, but it is not intuitive and cannot be made intuitive. The best we can do is learn to work with it, to calculate with it, to make predictions that match experiment, while accepting that we will never picture it the way we picture a waterfall or a flying bird. Understanding atomic energy means knowing that scientific knowledge is a light we cannot unlight. Once you know that mass is energy, once you know how to release that energy through nuclear fission and nuclear fusion, you cannot unknow it. The knowledge persists, and what we do with that knowledge becomes a question of wisdom, of ethics, of choices that go far beyond what physics alone can tell us. And understanding atomic energy means cultivating a sense of awe before the mystery. We have learned much about the atom without exhausting its secrets, because each answer reveals new questions, and each layer of understanding exposes deeper layers of complexity beneath. Let me be clear about what I mean by awe. Fear is not what I mean, though fear is sometimes appropriate. Worship is not what I mean, though the religious sensibility finds echoes in the physicist's experience of nature. What I mean is the experience of standing before something vastly greater than yourself, something that operates according to laws you did not write and cannot change, something that reveals your own understanding to be partial and provisional and forever incomplete. Scientists and mystics share this experience, approached from different directions. Mystics look inward and discover that the self dissolves under examination, that the boundary between self and world is more porous than common sense suggests. Physicists look outward, into the atom, and discover the same thing, that matter dissolves under examination, that the boundary between particle and field, between energy and mass, between observer and observed, cannot be drawn with any precision. Both arrive at a kind of humility, not the false humility that says we know nothing because we know a great deal, but the genuine humility that recognizes knowledge as partial, as perspective-bound, as one view among many possible views of a reality that exceeds any single description. I've read the Greeks and I find the Hindus deeper. Greek philosophy tends toward the definite, the logical, the binary, where a thing either is or is not and statements are either true or false. Hindu and Buddhist thought has long been comfortable with complementarity, though, with truths that depend on perspective, with the notion that apparent opposites may both be aspects of a single reality that transcends our categories. Modern physics vindicated this ancient wisdom through entirely empirical means. Wave and particle, energy and mass, potential and actual, these are not contradictions to be resolved, but complementary aspects to be held together. The atom teaches us that reality is stranger than either Greek logic or common sense can accommodate. The atom that once seemed the ultimate simplicity, an indivisible point at the foundation of matter, has revealed itself as a cosmos in miniature, with its own vast interior spaces, its own complex dynamics, its own relationship to the unimaginably large and the unimaginably small. Beyond the atom lies the quantum field, the fabric of space-time, the dark energy and dark matter that dominate the universe while remaining almost entirely unknown. This is the true nature of atomic energy. Not merely a powerful fuel or a dangerous weapon, but a window into the fundamental structure of existence itself. A reminder that reality is deeper than we can grasp, more unified than it appears, stranger than we could have imagined before we began to look. That is what the atom has taught us. Not that we are masters of nature, but that we are participants in a mystery far greater than ourselves. Not that we know everything, but that we have begun, barely begun, to see how much there is to know. And in that seeing, in that first glimpse of the depths beneath the familiar surface of things, there is terror, yes, but there is also beauty. A beauty both terrible and wonderful that makes the heart ache with wonder at the nature of all that is. The deep things in science are not found because they are useful. They are found because it was possible to find them. That is their truth, and it is also their tragedy.